This is the second video that I'm going to do on using polynomials to prove results in combinatorics. And unlike with the previous one, I'm not going to start with a theorem and then bring polynomials in afterwards. I'm going to start with a result about polynomials, and then we'll see a couple of applications of it. And the theorem that I'm going to talk about is something, it's a theorem due to Noga Alon, who's a very famous combinatorialist. Perhaps I'll just write his name. Somebody where his name sort of feels as though it's almost palindromic, but not quite. Not that that's very important. And the theorem is known as the Combinatorial Nullstellensatz. Because it's related in a way that I'm not going to talk about to Hilbert's famous Nullstellensatz, to be completely correct about the pronunciation. And I think I'll just launch straight in and tell you what it says. So let f be a polynomial in n variables, up to xn, over fp. And let a1 up to an be subsets of fp. And let the degree of f, so the total degree of f, be d1 plus dn. And suppose the following two assumptions. One, ai is at least as big as di for all I. And two, the coefficient of x1 to the d1, xn to the dn is non-zero. There's a non-trivial coefficient x1 to the d1 up to xn to the dn. The conclusion is then f does not vanish on a1 times an. So what do I mean by doesn't vanish? I just mean we can find some x1 up to xn where xi belongs to ai and f of x1 up to xn is not 0. So that's the result. And there's a short proof. It's not quite the same as Alon's original proof, which was also reasonably short, but it's due to somebody called Michalek. So let's give the argument. So it's going to be a proof by induction on the degree. So let's pick some a in a1. So we're going to assume the result for all degrees smaller than d1 up to d1 plus up to dn. And by the way, the base case when the degree is 1 is completely trivial, so I'm not going to even bother to show you how to do it. So we'll pick a in a1, and now we're going to do something that may be slightly scary at first, which is polynomial long division. So you're used to polynomial long division for polynomials of one variable. We're going to do polynomial long division in several variables, but I'll explain that that's not as worrying as it might at first seem. Maybe it doesn't seem worrying, that's fine. So we'll write f of x to be x1 minus a, p of x. X is shorthand for, by the way, x1 up to xn. So x1 minus a times p of x plus q of x, where q does not depend on x1. So let's see, just how do we do that? Well, we can just think of f as being a polynomial just in x1 with coefficients in the ring fp x2 xn. That's the ring of polynomials in x2 up to xn over fp. So we just do the normal polynomial long division, but just the coefficients of polynomials are themselves polynomials in the other variables. So you just, if you think about it, you see that you can certainly do that. Now, let's just restrict attention to the set A cross A2 cross up to AN. What do we find? We get that F equals Q on that set, and F vanishes. So it equals Q just because this term here disappears. So Q vanishes on A2 cross AN. So, but, sorry, Q vanishes on A cross A2, but Q doesn't depend on the first, on X1. So that means that Q vanishes everywhere on A1 cross AN. So that last conclusion was because it vanishes on one slice of A1 up to AN, doesn't depend on the first variable, therefore it vanishes on the whole thing. Just means it takes the value 0 everywhere here. So that means that we actually get that fx equals x1 minus a px on a1 up to an. Now what can we say about p? Well, remember that f has a term in x1 to the d1, xn to the dn. And so we've got some coefficient here that's non-zero, so lambda d1 to dn. What happens when we do polynomial long division and divide by x1 minus a? Or let's just have a look at this px. We can see that we've got to have, in px, the term in, we're going to get a term that looks like this, lambda d1 up to dn, x1 to the d1 minus 1, x2 to d2, up to xn to dn. Because the only way that we can, because f has degree d1 plus up to dn, the only way we can get a term like this, we can't get it from the a part because that would require p to have a term in x1 to the d1 up to xn to the dn, but then when we multiply that by x1, we get a higher degree term. So p must have a non-zero term in x1 to the d1 minus 1, x2 to, so p that satisfies, or so p basically what I'm going to say is P satisfies the hypotheses we need for an inductive hypothesis. So the degree of P is d1 minus 1 plus up to dn, which I've got to put in a d2 there to make it clear what I'm talking about, plus d2 plus. And it has a term in x1 to the d1 minus 1, blah, blah, blah. And last thing to observe is that P, because f vanishes on all of this set, we can deduce, and that x1 minus a does not vanish except when x1 equals a. We can deduce that px, or p rather, vanishes on a1 minus a cross a2 cross an. But now we see that by induction, well, this is a contradiction, because by induction, P can't vanish on this set because it has this degree and it has a non-zero term here. So I'll just say contradiction. So I started with the assumption that F vanished. Which I didn't actually, I didn't write that down, but so what I was doing here was assuming that F does vanish here and then contradicting an inductive hypothesis. Good. So we've got the combinatorial Nullstellensatz. Now let's see how to apply it. So I'm going to warm up with a reasonably easy application, and then I'm actually going to prove a closely related application that's slightly harder. But actually that'll give a slightly misleading impression, because the two applications are somewhat similar, but actually there's a very wide variety of applications, and some of those will be on an example sheet, just to give you an idea that it's not just a small variance of the two applications that I'm going to give. So I'm going to prove something called the Cauchy-Davenport theorem to start with. And I should say that the Cauchy-Davenport theorem has a reasonably easy proof that doesn't use polynomials, but it still provides a good illustration of how to use the combinatorial Nullstellensatz. If you've got any historical sense, you may know that Cauchy was sort of late 18th, early 19th century mathematician, if I got that right, and Davenport was very much a 20th century mathematician, mid 20th century. So how can there be a theorem due to Cauchy and Davenport? Well, it's just one of those typical stories that Cauchy proved it in something like 1819, I can't remember exactly, and Davenport proved it in about 1935. And then in 1947, I think it is, Davenport discovered that Cauchy had beaten him to it by over a century. And it somehow came to be known as the Cauchy-Davenport theorem. And here's what it says. Let A and B be subsets of Fp, P being a prime, and we write A plus B for the set of x plus y such that x is in A, y is in B. Then the conclusion is that the size of A plus B is at least whichever is smaller out of P, which is a sort of trivial case, and size of A plus the size of B minus 1. And where does this come from? It comes from the fact that if A is sort of the numbers from 1 to R and B is the numbers from 1 to S, then A plus B will be numbers from 2 up to R plus S, as long as R and S aren't too big, or R plus S is not too big. And then that's got size R plus S minus 1. So it's a very natural example that shows that it's sharp. Right, so now let's think, what on earth has that got to do with polynomials vanishing on sets and so on? So I want to try to convey to you here that once you've got the clue, use the combinatorial Nullstellensatz, actually, the proof starts to write itself. So it's not obvious in advance that a tool like that would be useful here. But once you know that you've given a hint, sort of please use that tool. We've got to think, first of all, we need to find some sets. So in the Cauchy-Davenport, in the Combinatorial Nullstellensatz, we had sets A1 up to AN. What are our sets going to be here? Well, we've got a couple of sets there. Not much choice, really. That seems the most obvious thing to try. So we're going to try to define a polynomial in two variables. And we want it to vanish on A cross B. So how are we going to do that? Well, we're given something about the sumset and the size of the sumset, and also we'd like its degree not to be too big. We hope. And we'd also like a certain coefficient not to be 0, but let's come to that later on. So how can we get a polynomial to vanish? So what that's saying is that for every x and y, we got that f of xy should be 0. Well, we ought to use the sumset somehow. And so one way of making a polynomial vanish is to make it a product of factors with the property that for every x, y, at least one of those factors will vanish. So what do we know about x and y? We know that x belongs to A and y belongs to B. So we know that x plus y belongs to the sumset A plus B. So if we take a factor x plus y minus c, where c belongs to the sumset, that will guarantee that f of xy vanishes for that particular, or will vanish whenever x plus y equals c. So what we could take is the product over all c belonging to, now we could say a plus b here, but just for sort of notational convenience, it's not a deep mathematical thing I'm going to do here. So this is with benefit of hindsight, it's just slightly convenient to do this where C is a set of size A plus B minus 1 that contains A plus B. Now we don't know that that exists because A plus B minus 1 might be too big. So I'm going to suppose, first of all, in order to make this work, let us suppose that A plus B minus 1 is less than or equal to P, so that we can actually do this. And I'll come to the case A plus B is greater than P. A plus B minus 1 is greater than P later on. So supposing we can do this, so then actually I think I would rather, I'm going to go for less than or equal to P minus 1, as a matter of fact. I think that's going to be important. So then what can we say about this polynomial? So we get that the degree of f equals I didn't mean A plus B minus 1. So I'm now supposing that the result is false. So if the result is false, that means that we can find, that means that A plus B has size less than or equal to A plus B minus 1, so it's A plus B minus 2. So I want to write A plus B minus 2 there, I beg your pardon. but we still may as well suppose that, because that's all right. So the degree of f is then a plus b minus 2. And f vanishes on a cross b because C contains the sumset, so x plus y belongs to the sumset. So one of those factors must be 0. And we just sort of think about the coefficient now. So the coefficient of x to the a minus 1, y to the b minus 1 is a plus b minus 2, choose a minus 1. Think about it, let's expand by the binomial theorem, we get this coefficient. But p is prime, and a plus b minus 2 is less than p. So this binomial coefficient doesn't have a factor p. So the coefficient is non-zero. And that's a contradiction. We've managed to find a polynomial that vanishes, but it's got the a non-zero coefficient and this degree here, and a has size. So we're doing it with d1 equals the size of a minus 1 and d2 equals the size of b minus 1. Getting a contradiction. So in the case that the size of a plus the size of b minus 1 is less than or equal to, or actually I could have had minus 2 less than or equal to p minus 1. Do I want that? Perhaps I do actually want that. So I need a plus b minus 2 less than or equal to p minus 1. So the alternative case is if the size of a plus the size of b. So we certainly proved it in this case because that's what I needed. I needed this to be less than p. The alternative case is that it's greater than p plus 1. In fact, no, I didn't need that extra thing, but I've got it. But that's so if a plus b has size at least p plus 1, then for any x, we get that the size of a intersects x minus b. Those are two sets that have size that add up to more than p. So let's sort of say that this set is not empty. So that implies that x belongs to a plus b. So in that case, we get that a plus b is everything. So a plus b has size p. So that's the other case, that if the size of a and the size of b are too big, then we get everything there. Okay, so that proves the Cauchy-Davenport theorem using the Combinatorial Nullstellensatz. Now we're going to prove a theorem of Silva and Hamidoune. It's actually a special case of a theorem they proved, which is about something that's similar to sumsets, but where we don't allow ourselves to add the same number to itself. So we define a restricted sumset B, so I put a little dot there. That's the set of x plus y such that x belongs to A, y belongs to B, and x does not equal y. And the question is, how small can that be? And the theorem is, again, they're subsets of FP. So that's in the background. We get that the size of a restricted sumset B is greater than or equal to the minimum. So it's going to be a bit smaller. because we're not including all the sums that we included when we took the entire sum set, and it turns out that we get a plus b minus 3. And let's have a look at one case. Supposing a equals 1 up to r, and let's suppose r is reasonably small, quite a lot smaller than p, then we get that a restricted sum set a is, well, we don't get 2 anymore, because the only way we can make 2, assuming r is less than p over 2 or something, is as 1 plus 1, and that's not allowed. So we go from 3, which we can certainly do, all the way up to, and then again we don't get r plus r anymore, because we can't make it in any other way. So we go all the way up to 2r minus 1, and we'll see that that is r plus r. I mean, the size of this set is the size of a plus the size of b minus 3, which is one of those things that's horrible to check. But if we just think about, it's the same as the size of the set from 4 up to 2r, so then we can see that it is everything up to 2r except for 1, 2, and 3, so it has the size 2r minus 3. Okay, so that just shows that it's certainly sharp, at least some of the time. Now then, let's set about proving this. So I think I'm going to do the case, first of all, the sort of simple case first. So if size of A plus the size of B is greater than or equal to, turns out to be convenient to say P plus 2, then what can we say if I just pick some x in FP? We get that the size of A intersect x minus b is greater than or equal to 2. So we have at least 2 ways of writing x as A plus b. Now, p is prime, so there's only one way of writing it with A equals b at most, and that is just A1 equals B1 equals x over 2, or the inverse of 2 times x. So it must be possible to write x as a sum of distinct elements, 1 from A and 1 from B. And so that in this particular case, we get that the restricted sum set is the whole of FP, and therefore we have this P here. So from now on, let's assume that assume that the size of A plus B is less than P plus 2, because otherwise we're done. Right, now let's define a polynomial. So what on earth are we going to do here? Well, it turns out that there's a simple answer to this. So let us, first of all, let C be a set of size A plus B minus 3 that contains, and notice that that's less than P, but in fact it's less than P minus 1. I may want to change that to P minus 1, but we'll see later on. That contains the restricted sum set. So now the obvious thing to do is to write fxy exactly the same as before. So product over all C in C of x plus y minus C. So does that vanish on the on A cross B? Unfortunately, it doesn't, because, or doesn't necessarily, because if x equals y, then we have no reason to suppose that there is a c in C that equals x plus y, because that x plus y doesn't belong to the restricted sumset A plus restrict dot B. Or it could do, but we don't know that it does. But I mean, it could do if there's some other way of writing 2x as a sum of things in A and B. But we can't be sure about that. So we have to do something to make it vanish when x equals y. And I think I only have to say that for it to be blindingly obvious what we do. We just make it vanish if x equals y. We just stick a factor x minus y on the front. It's almost embarrassing, but there we are. That's all we have to do. And now the rest is just going to be a kind of check. So then we certainly have that f vanishes on A cross B. We also need the degree to be something or other. So what is the degree? The degree of f is A plus B minus 3 plus 1, because we've got this extra factor, which is great. So that's A minus 1 plus B minus 1. So we'll be in great shape as long as we can show that the coefficient of well, x to the A minus 1, y to the B minus 1 is non-zero. But I've just done something wrong here. I'm hesitating because, again, I've made the mistake that I was almost made last time. I want to assume for a contradiction that the size of the restricted sumset is less than A plus B minus 3. So I can assume that C has size A plus B minus 4. So the degree of f is actually minus 4 plus 1. So it's that minus 1. This is actually very important. So I will be done if either the coefficient of x to the A minus 1, y to the B minus 2 is non-zero, because then I can take d1 to be size of A minus 1 and d2 to be the size of B minus 2, or the coefficient of x to the A minus 2 and y to the B minus 1. If one or other of those two coefficients is non-zero, then I'll be in good shape. So let's just see what those two coefficients are. It's ever so slightly more complicated than in the previous proof. So what's the coefficient of x to the size of A minus 1? Well, we can get times y to the B minus 2, we can get it in two different ways. So we either get it from x to the A minus 2, y to the B minus 2 times an x, or we get it from x to the A minus 1, y to the B minus 3 times a minus y. So, and this is, this part here has degree A plus B minus 4. So let's first of all work out what the x contribution is. So that's x to A minus 2, y to the B minus 2. So that gives us binomial coefficient A plus B minus 4. Choose A minus 2, and that'll be minus a plus b minus 4, choose. So this time I'm going to have a minus 1. So just tell you where those numbers came from once again. For the first coefficient, I wanted to get a power of size of a minus 2 for the x, which I would then multiply by an x. For the second one, I wanted x to go down by, x to go up by 1, because I'm not going to multiply it by x anymore. And then y will correspondingly go down by 1, and then there's a minus sign here because of the minus there. So I get that a minus 1 is because I now want the power of x here to be the full x a minus 1. And let's just do something very, very similar here. It'll be a plus b minus 4. So this time, to get the a minus 2 thing, I'll either start with an a minus 3 and multiply it by x, or I'll have an a minus 2 and multiply by minus y, so I get this minus, and an a minus 2 for the x. So we want to prove that one or other of these two things is non-zero. Now, if that's not the case, that tells us that this binomial coefficient equals this binomial coefficient, and this binomial coefficient equals this one. And I notice that this one is this one. So that tells us that there are 3 consecutive binomial coefficients that all are the same. And so the only thing to do now, just to finish off the proof, is to show that that can't happen. Claim if r is less than p, then we cannot have r choose s, let's say, equals r choose s plus 1 equals r choose s plus 2 mod p. Let's just, to do that, let's just remember what r choose s over r choose s plus 1 is. It's, so we had that in an earlier section. I always have to work these out when I'm doing. So we have an extra s plus 1 in the denominator on the bottom, so that ends up on the top. And here we have r minus, the other one stops, is an r minus s minus 1 factorial, whereas here we have an r minus s factorial. So we get an extra r minus s factor, so we get that. So when are those two binomial coefficients equal? If and only if s plus 1 equals r minus s. And now substituting s plus 1 for s, I'll get the other two are equal if and only if s plus 2 equals r minus s minus 1. And adding 1 to both sides, that tells us that that's equivalent to sort of s plus 3 equals r minus s. And so there we get that s plus 1 equals s plus 3 mod p. And that we don't have unless p equals 2, and I leave it to you to check that the whole theorem works when p equals 2. There's not very much to sort out there. And therefore, we are done. Maybe there's a sort of tiny, the reason I hesitated slightly, there's a sort of tiny little maybe worry one might have about what happens if the size of a is actually less than 3, so that this is a choose minus 1. That's not such a problem. We just, the binomial coefficient is by convention 0 in that case. But also you can actually see that it's not very hard to prove that if the size of a is less than 3, well, let's just go and have a look. What does the theorem tell us? lost it. Here we are. If A has size less than 3, then it's got size at most 2. So we're trying to prove that the size of this thing is at least the size of B minus 1. And if I just pick one element of A, then I'll certainly get all the possible sums with that one element. So that's B possible sums, of which only one is ruled out because I've taken something that equals that one element of A. So we certainly get at least B minus 1 here. So we can actually not worry too much about the fact that A might have size less than 3. So that completes that set of proofs. And I'm afraid I'm slightly sort of, just a sort of little comment at the end, I find these applications a little bit mysterious. So for example, a kind of question I don't have a good answer to, and if anybody thinks about it and comes up with a good answer, please feel free to get in touch with me. So why, you can sort of see in hindsight that you can apply the method, but it doesn't seem completely obvious that when you apply the method, out pops the absolute best possible result at the end. Is there some reason that you would expect in advance that when you apply this particular tool, you'll get an optimal result for these problems, rather than just some pretty good bound or something? As I said, I don't have a sort of convincing answer to that. I don't also have a particularly convincing, from time to time, I think I've sort of spotted, and perhaps I could use the combinatorial Nullstellensatz because there's some Cartesian product floating around. But in general, I'm still at the stage myself that sometimes there's a problem where if you have the clue that you want to use the combinatorial Nullstellensatz, then you can sort of work out there's only one reasonable way to use it. But sort of spotting in advance, oh yes, this is the sort of problem where the combinatorial Nullstellensatz would be useful. That's a sort of level that I've not yet reached. I encourage you to try to reach it in a way that's better than I have. With that, I will finish this video, and next time we'll have one more absolutely wonderful proof using polynomials.